Okay, so now let me introduce you to tonight's speaker. We are thrilled to have Munir Humayun, who is an FSU professor of geochemistry, a researcher at the MagLab, and an expert in cosmochemistry. He studies meteorites using the lab's sophisticated arrays of spectrometers, and tonight he's here to talk to you about Mars, a meteoric, I'm going to mess up that word now, a perspective on meteors, how about that? So I'll hand it over to him, and stay afterwards. He's brought a microscope and a sample with him, so make sure to stay and experience all that Science Cafe has to offer. Thank you guys.
I brought some meteorites with me. I'm going to pass a few of them around. This chunk that I'm passing around is an iron meteorite. This is what most people are familiar with when they hear about meteorites. It's nice and heavy. It's loaded with elements like iridium and nickel. So I'm going to hand it at the bar, make sure it comes back to me. This specimen is Canyon Diablo. It made meteor crater in Arizona. And the other specimen that I have here is Jebel Camille. It's a very nickel-rich iron. This one's very nicely shiny cut and polished. And it was recovered from Egypt. And the third specimen I'm going to pass around is Gibeon. This looks like a nice square-cut specimen. It's been cut, polished, and etched. And when you look at it, you can see two different nickel-rich minerals in it that form in cross angles named the Widmann-Statten pattern, a very diagnostic feature of iron meteorites. None of these are from Mars, by the way. The one from Mars I'm going to show you at the end, and that one is very special. Anyway, today I'm going to speak about Mars as a planet, what we learn about from meteorites contrasted with what NASA finds out from space missions. So Mars, of course, is the red planet, and you see it here in the foreground, and Earth is over there. And if you look carefully, you can make out the Saudi Arabian Peninsula, and then to that side of it, you'll see North Africa. And that's the Sahara Desert, and the Sahara Desert plays an important role in our story because the meteorite I'm going to talk to you about, that much of our really interesting Martian meteorites are now coming out of the Sahara Desert. Now, when I first set up this talk, I realized that people in the back are not going to be able to see the bottom of the slide, so I've tried to put all the most important information near the top of the slide. This is an image of Mars over here, and it's a Mercator projection, just like the famous ones you see of the Earth, where Greenland looks really, really big and Canada is humongous, and if you're close to the equator, things look a lot smaller. To prevent that effect, it's been truncated at about 70 degrees north and 70 degrees south. What you're seeing here, color-coded, is the topography. So this is the height above a reference point at line 0. Between the colors of yellow and green, that's the 0 reference line. And the blue stuff that you see in the north is about 4 kilometers on average below the reference line. And the red stuff that you see in the south is about 4 kilometers high relative to the reference line. And so on Mars, you're looking at topography of about 8 kilometers. And so if you had to walk from where Viking 1, and you had to go all the way to the top of Olympus Mons, you would have to climb about 10 kilometers or so. It's quite a run. Anyway, what I want you to do is notice that Mars has this feature called the crustal dichotomy. The dichotomy refers to the fact that the south is all highlands and the north is all lowlands. It's flat, there's not a lot of mountain on it, and not much cratering on the northern portion. The south, everything is heavily cratered. And this cratering is a relic of Mars's birth, and it's part of the evidence for the southern hemisphere being very ancient. This would not be preserved if the geology of Mars allowed the surface to planet to resurface itself. For example, if you look over here, there are a lot of volcanoes. This area looks very smooth, and that's because volcanic lava flows have poured over the old craters, and they have erased the craters. In the north, the craters have mostly been submerged underneath sedimentary cover, and so you don't see craters as abundantly in the north. But this old stuff here has to be older than about 4 billion years. More than half of Mars is that ancient. In the next view graph, I'm going to show you the poles of Mars on the same scale. And now you can see the crustal dichotomy very clearly. That's the North Pole, that's the South Pole. 4 kilometers below average, 4 kilometers above average, a difference of 8 kilometers. What you're seeing here, heavily cratered South Pole, there's no data on the very center, but you can see the ice pack. This is the carbon dioxide and water ice pack around it. There's a North Polar cap over here that's basically carbon dioxide and water as well. And you can see it in various stages of erosion, which creates the features around the edges of the ice pack. But just like the Earth's poles, it has a permanent ice cover on it. Now, there are many important questions we've always wanted to know about Mars. There's Marvin the Martian, standing on a view graph that was taken by the Pathfinder mission, and he's looking at his rocks and wondering, what are the important questions? Well, everybody wants to know if there's life on Mars. I'm not going to be able to answer that tonight. But before you can answer that question, you have to know if there's water on Mars, because there's going to be no life if there's no water. At least life as we know it. Okay? And so, is there water now or in the past? And that's an important question, and it's being addressed by things like the rovers that are finding abundant evidence for traces of water. I'll show you some evidence for water as well. Is there volcanic heat source on Mars? If there is active volcanism on Mars, there is heat, and if you have water and heat, you get something called a hydrothermal system that gets going. It's thought that the Earth's life originated in hydrothermal systems in volcanoes on Earth. Now, if there is active volcanism today and a source of water, even if it's permafrost near the surface, it will melt to death, and you could have microbes living in the volcanic hydrothermal systems. There's the general question of how did Mars form geologically? And finally, perhaps that's what Marvin's wondering about. How much is this real estate going to be worth? Because of all the planets in the solar system, this is one of the first planets we would try to colonize. Mercury is too close to the sun, too hot, too cold at night, too hot by day. Venus is a burning planet with an atmosphere so crushing that it's hard to get even robots to it, and its atmosphere is made of sulfuric acid, which dissolves and destroys corrosively just about any piece of equipment we have. So Mars is a place where you can send robots. The atmosphere is thin. It is too hard for a camel to breathe on Mars because the atmospheric pressure is about 0.6% of what the Earth's atmosphere is. It's equivalent to being 70 kilometers up in the Earth's atmosphere. As you know, you cannot breathe at those altitudes without at least some kind of space mask. So we'd have to do some terraforming if we're going to live on Mars. Now, to answer questions, you need sources of information. And the kinds of information we have most famously, of course, are the fact that spacecraft and robotic missions have visited Mars. And we have the Viking spacecraft that landed there in '76. We have the Mars rovers that so famously have trotted around the surface of Mars. And we now have the Mars Science Laboratory, or Curiosity. And Jen Stern gave a talk in one of our science cafes on the recent results from that. What these missions give us is the basic chemistry of Mars. They tell us the big picture, they don't really get to the details of the chemistry. What we really want to know about Mars has to come from samples that are picked from the surface and returned into laboratories on Earth where we can study them. Well, incidentally, there are meteorites from Mars, and they provide us with an incredible level of chemical detail that we can access before samples even come back from Mars. Now, Marvin doesn't like that, okay? He says, you're kidding. Did you really say there are meteorites from Mars? And this is what I've got to tell Marvin. Yes, Marvin, there are meteorites from Mars. All those rocks you keep blasting with your laser blaster, where do you think they go? Alright, well, it so happens that meteorites from Mars have been known for decades. They were known long before we knew that they were Martian meteorites. When we get meteorites, most of our sources of meteorites, like the 3 irons that I'm passing around, they come from somewhere in the asteroid belt. And asteroids are very small, and the time when you can volcanically melt asteroids is very early in the history of the solar system. So when you radio date an asteroidal rock, you get an age that's older than 4,500 million years. That is, all asteroidal samples are extremely ancient. Now, on Earth, you'll never find a rock that's this young. So fancy, you find this rock that falls from the sky and you measure it and it has an age of say 150 million years. Now if you want to know what's 150 million years in Earth history, that's a time when we have dinosaurs on Earth. For example, T-Rex. So you have these really young igneous rocks that all have a chemical relationship to each other, and they form a real puzzle in interpretation. They must come from a planet because there are no young asteroidal basaltic rocks. Basalts, by the way, are volcanic rocks generally produced on planets. So we find them on the Moon, we find them on Mars, we find that the surface of Mercury is covered with them. 2/3 of the Earth's surface is actually covered with basaltic rock, but most of it's under the sea. And so you don't see that much basaltic rock, certainly not in Florida. But you'll see it if you see it upstate New York, the West Coast, but they seem to be rare on the continental crust. However, they cover the surfaces of most planets. And what's surprising about these meteorites is that you see this class that ranges from some 600 million years to about 150 million years ago. And that age span indicates that it has to be a very large body from which this is coming. They can't come from Venus, it's too big. It's got too strong a gravitational field and its atmosphere is so crushing that if you try to pick a rock up and accelerate it out to space, it would burn on the way out. You can't bring them from Earth because they're definitely not Earth rocks. You can't bring them from Mercury because you can knock something off Mercury, it falls into the sun. It's way too close to the sun to accelerate something all the way out to the orbit of the Earth. But if you knock something off the surface of Mars, it doesn't have enough of an atmosphere to stop it from escaping. It has a very small escape velocity. It's 10 times less massive than Earth. And so its escape velocity allows meteorites or fragments of rock to get into space, and then they spiral towards the sun, and they just so happen that Earth gets in the way from time to time, and they fall on Earth and we pick them up. But how do we really know they're from Mars? That's a speculation. The situation changed dramatically for science. In 1983, when this meteorite was studied in detail, it's got the name ETA 79001 because it was collected by the US Antarctic mission in Antarctica, and this stands for Elephant Moraine, year of collection 79. This was the most interesting sample, so it got the number 001. Now, I would prefer to have 007 myself, but alright, this guy is privileged with being the first of the 1979 collection to be looked at. It's a basaltic rock, and it turns out to have an age of 170 million years, just like all the other shergottites I showed you earlier. But what's unique about this, or was unique about this, because we have several samples of this now, these pieces of black materials that you see in here. This is shock melted glass that is made when vesicles that are inside the sample collapse during the shock, and they trapped atmosphere inside them. And when you take this glass out and you get the atmosphere that is trapped in it out into a mass spectrometer and measure it, it has a striking resemblance to the measurements of Mars's atmosphere made by the Viking lander mission in 1976. There's a trick here, alright? So I'm going to show this graph rather carefully. If you're not used to looking at graphs, you won't pick this trick up. On this scale, is shown that the data coming from ETA 79001 on this scale is the data from the Martian atmosphere. In both cases, they are the logarithm of the number of gas molecules per cubic centimeter. In the case of the Martian atmosphere, that's an actually measured quantity. So there are something like 10 to the power 17 molecules of carbon dioxide per cubic centimeter of Martian atmosphere. I can assure you that level of gas is not found in those little vesicles that I showed you a picture of. Instead, you find some level of gas and you scale it at nitrogen and say, supposing they have the same nitrogen, what does the pattern look like for the rest of the gases? And when you do that, it makes a very nice one-to-one line. The carbon dioxide comes very close, the argon comes very close. Those are the three main constituents of Mars's atmosphere. They're not the three main constituents of the Earth's atmosphere. That would be oxygen, nitrogen, and incidentally argon. But when you look at the abundances of all these other gases, they line up very beautifully with Mars. And so this became the rock that clinched the argument that these samples had to come from Mars. And so ever since 1983, we have known that we have basaltic rocks in our collections that represent Mars. We've been able to study them, and in these detailed studies, we've built a picture of Mars's volcanic history. Then, Mars rovers go to Mars, they bring sophisticated X-ray spectrometers, they measure rocks on Mars in place, and they find out they don't look anything like our sugar-type meteorites. But remember, Mars has the crustal dichotomy. What are we looking at? Anyway, one important thing about Martian meteorites is that most of these Martian meteorites are found on Earth. They're not really seen to fall. About 4 or 5 of them have been seen to fall. So we have observed them, but most are found in Antarctica. And when the Antarctic meteorite program began in 1977, the return of these sugartites was one of the more exciting things. And you see year and number of samples. We get one every few years, sort of crops up. And we haven't seen one since 2007 from Antarctica. It's not that collections haven't been done every year, it's just that they have not yet returned another sugartite. On the other hand, in around 2000, the first attempts were made to go and look in the Sahara. And what motivated this was that collectors of meteorites, who are generally very wealthy people, wanted to have a sample of Mars in their collections. And they couldn't get them from the US Antarctic program because every sample collected by the National Science Foundation is property of the government of the United States, which means right now, nobody can get access to it. Alright? And they're never for sale. Unlike, say, American military aircraft and other things like that, which foreign countries can buy, you cannot buy a Martian meteorite even if you're a multi-billionaire. So what do you do with your billions? You ask people, well, do you have a Martian meteorite? And they start scratching their heads and going, you know what? If they fall in places like Antarctica, they must fall in the Sahara Desert too. And no one's looked. So they brought some sugartites to Bedouin tribesmen and showed it to them and said, ever seen a rock like this in the desert? I'll not be willing. I've seen lots of such rocks. What? I make a campfire out of them. Well, next time you see one of them, you mind bringing it into Morocco and we'll talk in the Kasbah. So the Bedouins started bringing the rock samples in, and what you can see is this enormous collection. Very rarely do you see just one sample, but there have been as many as 4 samples coming in every year. This is an enormous return from the hot deserts of the world. Some come from Oman. This one was found in Los Angeles, but basically most of these things are now coming out of the Sahara Desert because the tribesmen have learned to identify them. That means all over the world there are other places where these meteorites must be available, and there just nobody knows to pick them up. You want to know how much they're worth? These tribesmen started out on camelback and they now all drive SUVs because these things fetch a price of about $2,000 for a gram of meteorite. Alright? Now, for comparison, you've heard about something being worth its weight in gold. Do you know what the price of gold is? About $45 a gram. Alright. Anyway, the strategy that I have named this is called Better on a Camel. And this has a history. In the old days, there was an airline called, before it was called British Airways, it's called British Overseas Airways Company, or BOAC, and was very affectionately known for its bad service as Better on a Camel. You may be aware that Delta Airlines has a similar acronym. It stands for Delay Everybody's Luggage to Atlanta. Anyway, I'm not sure if that's in the Delta official history, but this is definitely in British Airways official history. What you see here is one of the original British Airways aircraft. This is a de Havilland DH-3 taking off in Lagos. And the Emir of Lagos would send this gentleman to blow this horn to warn the camel train so that they wouldn't spook the camels as the aircraft took off. These days, camels are used to aircraft. So, Better on a Camel, meteorites from the Sahara Desert, is how we get our meteorites. Here is a genuine Tuareg tribesman in the blue robe. He covers his head in the turban. One of the reasons for keeping your mouth covered all the time is, of course, there's a lot of dust. And this is one way to keep the dust out of your mouth. This, for comparison, as you can tell, is an American. The difference between an American who's disguised as a Tuareg so that he can travel in the desert and not be arrested by the local police as a meteorite collector, and the original Bedouin tribesman is how they cover their face. The American covers his eyes and leaves his face exposed. You notice that the Tuareg tribesman covers the rest of his face and he leaves his eyes exposed. It's better for keeping an eye on your enemy. Anyway, imagine having to deal with guys like these and trying to negotiate the best price you can for your meteorite. You have to understand, these things are definitely worth $2,000 a gram, because I wouldn't try to pay that guy any less. Another thing I want you to notice is that the Sahara Desert and Mars look very similar. They're sandy, they're very brown or yellow, and there are rocks all over the surface. Sometimes, even on Mars, you'll see sand dunes everywhere. So this is a picture of Marvin standing on the surface of Mars from Pathfinder, and this is a picture of Mike Farmer, a famous meteorite collector, standing in Erfoud in Morocco. They look so similar that anybody who was, say, a wealthy Arab would easily want to buy a piece of the real estate if you showed him that picture. Now, how can you tell which picture is Earth and which picture is Mars? It's human, that's right. That's one way to tell him. So if you don't see a camel in it, look at the sky. It turns out that Earth has a dense atmosphere, and as light filters through that atmosphere, you get something called radio scattering that makes the sky blue. Mars has a very thin atmosphere. It would be rather dark if it wasn't for the fact that the Martian atmosphere is filled with a very fine dust, and this dust scatters sunlight like mirrors, and that causes the Martian atmosphere to look kind of whitish. And that's how you can tell which picture is genuinely Mars, which picture is genuinely Earth, unless you have a cloudy day in the desert. Now, one of the paradoxes that we had encountered very recently with the return of all the data from Spirit and Curiosity is that the rocks that your typical rover saw on Mars were very different from the meteorites we get back on Earth. And it seemed like a very unique coincidence that this should occur. How could it be that meteorites, which must come from random events, end up not representing the most common type of rock on Earth? And why was it that only rarely the Mars rovers would encounter a sample that looked at them, well, it looks a bit like a sugartite meteorite. And we were scratching our heads on this and saying, well, statistics of small numbers. And that was until last year when this sample came back from the Sahara Desert. It was originally purchased by a very wealthy American in Morocco. He is a billionaire. He bought 3 stones, realized that they were unusual, brought them to the University of New Mexico, and a large team at the University of New Mexico went to work on it, and they realized that it was a unique meteorite, and they claimed it came from the Amazonian of Mars. The Amazonian is a period at about 2 billion years ago where there appeared to be running water still on the surface of Mars. And among the unique things they did was the radiometric ages came out at 2 billion years. Definitely not an asteroidal basalt, but very much older than those sugartites I showed you, which were as old as 600 million years. A lot older. A potassium-argon age came out at 1.6 billion years. Still very old. They concluded that this was a volcanic breccia. You've seen explosions of volcanoes where the volcano bursts out and produces a huge fire cloud. And the fire cloud then descends on the ground, and this is what happened, say, in Pompeii. Rocks, fragments, melt, all came together, and they produce a rock that's called a volcanic breccia. And they realized that this was a breccia. There were many different pieces of other rock trapped inside the matrix. And they interpreted it in those terms. They found it was very water-rich, and they realized that the chemistry was very different from the sugartite meteorites and very similar to your typical rock on Mars. And this came as a real big surprise because we finally had something that Curiosity or Spirit or one of the other rovers were looking at on Mars, and we had a sample of it in the laboratory. And so you can imagine the kind of excitement that this would generate. Well, my colleagues at the University of New Mexico who got the sample decided they want to keep the sample in the family. So when I heard about this sample, I went to them and asked them, would you please give me a sample? I want to measure these unique elements called siderophiles in there. Well, yes, we'll give you a sample, they said, but sometime down the future. I wrote them an email. I contacted different members of the team. I asked everybody for a sample, but the sample just wasn't coming. So I complained loudly, as we all do when we don't get what we want. And I was sitting, not like indifferent as you were, at a dinner here, and I asked one of my colleagues from France, I was telling her about how unfortunate it was I couldn't get this sample because I really wanted to study it. She said to me, well, Munir, we happen to have a sample of this. I thought, you've not heard me. This is a unique meteorite. There are only 3 stones in the world. It's all controlled by one mafia. So she didn't say anything more, but she came over to visit, and she said, I have a gift for you. Yes.
Wow.
Oh, yes, let me just point out, this is a dead ringer for Martian composition. So, you may not look at plots like this every day as I do, but this is the ratio of magnesium to silicon, the 2 most abundant elements in a rock, versus the calcium-silicon ratio. The silicon is the most abundant element, calcium and magnesium are the next 2. And when you plot one against the other, all the snake meteorites fall on this line. All the analysis of soils from Mars plot off it. All the rocks coming from Pathfinder and all of the Spirit and Curiosity plot way off that. Why is that? You know, we've been scratching our heads about it, and guess what? This meteorite falls right over all of the Spirit analysis. And so that's one of the things that made it so exciting about it. It's a dead ringer for common meteorite, for common rocks on Mars. Here's a picture of it in detail. I'm going to show you a piece of this sample so you'll be able to see these chunks of rock, white rocks over here, dark rocks over there. They're a whole bunch of different rocks that represent different kinds of formations in the mountains of Mars that have been ground up, hammered by meteorite bombardment on Mars. And the hammering has produced this powder of rock. And this rock powder has been cast by the meteorite. Every time a meteorite impacts into the crust, it produces powder that goes flying hundreds and hundreds of miles, even thousands of miles away. And if you're in the southern highlands where meteorites keep, where you're seeing an ancient time where lots of meteorites had hit repeatedly, every piece of ground is covered by meteoritic debris and rock debris that's drawn from all over Mars, from thousands of kilometers around. And then it's been compacted into a single sedimentary rock, and a piece of that rock has been blasted off. One way you can recognize how prolific the impact is to look at one of these dark clasts and see that the dark clast itself is a piece of an older sediment that has little white clasts in it. The white clasts appear to be igneous pieces of rock, and you can see these broken outlines. I have a piece of a shorgotite sitting at the microscope over there, so when you're done here, one of my graduate students will show you. Evan, if you'll just raise your hand in the back there, he will be by the microscope. He will show you one of these shorgotites, and you'll be able to see what a rock looks like that's not a breccia. And then I'll show you a piece of this that is a breccia, and you'll be able to see the difference between them very clearly. And how it got here, well, it turned out there weren't 3 stones. There were actually 5 stones found by the Bedouin, and they had sold 3 of them to an American and 2 to a Frenchman. And this Frenchman over here, Luc Leben, he's a dealer in meteorites. This is his website. He's holding another meteorite there. It's a lunar sample, and he has a picture of a moonscape behind him. But he paid about $50 a gram for this from the Bedouin, and he brought it to the museum in Paris. He happens to live in Paris, and this is my collaborator Brigitte Sonda and Roger Huens and a group of other scientists I work with routinely on a different project, and they're busy talking about the results of that project in France, and they asked themselves, well, what shall we do with this? Well, Munir seems to be interested, so they brought me a piece of it, and that is a picture of me holding about 100 grams of this meteorite. Once we analyzed it and showed that it was not what they thought it was, he paid $50 a gram for, it's now worth a small fortune, and that piece there is worth between $1.5 million. So let's just say you get a huge return on your investment if you buy meteorites, especially if you buy them intelligently. It's better than the stock market, and this is why millionaires everywhere are buying meteorites and not stock. All right. So I'm going to show you some chemical data that we collected. And here you're seeing plots of the elements nickel and iridium against magnesium. In your typical earth rock, nickel correlates very nicely with magnesium, and in the black field, that's where all the shergottites plot. And you get a nice correlation between the nickel and the magnesium. So you know exactly how much nickel should be in a rock if you tell me the magnesium content or vice versa. What's important about this is that most of the nickel and iridium in a planet is not in the crust of the planet. It's sitting deep in the core, and that's what iron meteorites are. They're pieces of asteroidal cores, and so those iron meteorites that I passed around, they're loaded with nickel and iridium. And so when they strike a planet, you can see their telltale signature from the amount of nickel and iridium that's left behind. Now, in the blue field over here and up there, you see the nickel and iridium contents that we see in lunar breccias. Lunar breccias are those rocks that make up the old crust of the moon, and they're the products of taking moon rock and grinding it up with meteoritic hammers and putting all this nickel and iridium back into them. And so they are recognized by having very high abundances of nickel and iridium. One of the strange things is that the blue and orange, these are soils from Mars that have been measured from rocks and soils respectively, measured by the Spirit rover on Mars. And what you see is that the nickel contents are way higher than the shergottite meteorites. Of course, this annoyed all the people who were on the Spirit team, and they kept telling the people in meteoritics, you guys have nothing to offer us. Our rocks are very different from the things you're studying in the laboratory. They're not analogs. Look at all this nickel we're seeing. What do you make of that? And everybody scratched their head and went, well, we don't know what to make of it because we don't see anything in the meteoritic record. Are you sure you calibrated your detector properly? Anyway, while they're arguing about it, you will notice that the range in the Martian soil is very similar to the lunar breccias. One might have speculated from this that this was meteoritic debris distributed all over the surface of Mars by wind. What I'll show you next is analysis of the sample that we did that shows the nickel contents in the fine-grained portions, those gray regions in the rock, and you can see that the nickel contents are all the way at the top there, the highest level seen in lunar breccias. So these are very similar to the samples brought back from the moon that represent intense meteoritic impact. And you can see the same thing in the iridium here. Very high concentrations of iridium, well above anything seen in any kind of shergottite meteorite previously. So this tells us that it's not a young volcanic rock. This is part of that ancient cratered highlands terrain. What came as a big surprise was when we looked at the rocks that looked like white clasts. The white little pieces of rock, they look like single pieces of igneous rock, but they have very high nickel concentrations at a given value of magnesium and very high iridium concentrations. Rocks on Earth, for example, in the Earth's mantle, have iridium somewhere about here, but they also have magnesium somewhere about there. They plot just where the Mars samples plot. What this tells us is that every piece of rock that we see in there, even things that look like igneous clasts, turned out to be impact melts. And that means that you melted rock to make new rock. You ground up rock to make new sedimentary rock. You ground that up again to make this rock that we've put together. This is a rock that's seen multiple episodes of impact, not one episode of impact. And it came as a big surprise because this level of detail has actually never been done on all samples. And the reason for that is the kind of tools we have, the kind of tools we have today, we didn't have back in the lunar days. And so I haven't been able, I'm going to do some of this on lunar samples to see if we see exactly the same thing there. And what we draw from this is that the chemical analysis demonstrates this is a regolith breccia. That's the regolith is the soil that covers a planet formed by impact. And so a regolith breccia is this collection. Sorry, I'm losing the microscope a lot here. Sorry, microscope. Anyway, it's fragmented Martian rock and soil that's been mixed with meteoritic impacted debris, rich in nickel and iridium. There's only one problem, folks. It should not be 2 billion years old. It should be 4 billion or older. And if you remember, the New Mexico group measured ages, and they got 2 billion year ages, and they told us, sorry, wrong number. Anyway, so one of the things we then had to do ourselves was find another way to date the samples. And the most robust way of dating samples is to look at these minerals called zircons. Zircons are little time capsules loaded with uranium containing essentially no lead. The uranium decays to lead with time, and so the lead accumulates, and by measuring the accumulation of the lead, we can tell how old these samples are. And because they are so rich in uranium, you don't need to take a bucket full of zircon to measure it. You can take a device called an ion microprobe with a beam spot. That's a 10 micron spot. These are very tiny crystals, and with a 7 micron beam spot, we're able to go in and measure the ages spot by spot. And when we do that, I've tied in the analysis. Here is a fairly large zircon grain. That's a 20 micron scale bar. A hair, for comparison, is about 30 microns wide. And so this is about the width of a hair over here. This zircon grain would be a little speck of dust inside your hair if you were looking at it with a naked eye. Anyway, with the ion microscope, it looks like this giant rock that you can take multiple measurements off. All those measurements plot over here in the air ellipsis. And the way this plot works is a zircon that's
I have a different mic. Hold on.
Well, I think I can get transmission sometimes. Anyway, let's try it.
Keep going, I'll set it up.
That's 4 billion years old would plot here, 3 billion years over here, 4.5 billion over here. These are plotting just shy of 4.5 billion years. These zircons were made in impact melts 4.5 billion years ago. And so the ages that had been produced by the New Mexico group were in error. And so I say, oops, uranium-less zircon ages, the precise age is 4,426 million years old. But there's a wrinkle to this. If you're on a planet that's being impacted over and over again, your time capsules are going to leak. You're going to break the bottle open. It has to reseal at a later date. And then it records a new age. And that causes the zircon analysis to plot down along a line like this and intercept at another point here. Excuse me. High-pitched voice there. Anyway, this is another zircon. You can see two analysis plot nicely here where all the other parts of the crystal, but there are younger portions that plot here and other zircons that plot all the way down here. It was disturbed at 1.7 billion years ago, which is very close. It splits the difference between the potassium argon and the rubidium strontium age determined by the New Mexico group on the entire sample. So this is a rock that has the ancient components like nickel, iridium, and old zircons in it, but it has a complex age history. It remembers part of its birth, and it remembers another event, perhaps a big impact on Mars at this time, at 1.7 to 2 billion years ago, that probably cemented the rock together and compacted it. So now we know we do have a piece of the very most ancient crust of Mars. When you look at this and ask, what's the difference between the soil then and the soil that Curiosity, for example, is measuring now, there are a handful of chemical differences. And they come down to just this. 3 elements. Sulfur chloride.
Here. Trade with me.
Go back to the come down to this.
Trade with me. Sorry, technical difficulties. Hold on. Try this. Don't get too close to this so that it doesn't frequent.
All right.
Yeah. Try that. How about that?
This is better than being at NASA. It's all right. It would take time. Anyway, there are 3 elements that are strikingly prominent and rich in the soils relative to the rocks on Mars, and they are sulfur, chlorine, and zinc. And they are observed in the Martian soils, but they're completely absent in our chemical analysis. Completely being somewhat qualified over here. For example, we do see very high levels of chlorine in our analysis, and our analysis is now along the green line. Your typical Martian rock or soil is in the blue circles over there, or the orange dots, which are the soils on Mars, and you can see they're a lot higher. All the chlorine in our samples comes because we have a single mineral in there that's an igneous mineral. It's called chloroapatite. And it contains chlorine and phosphorus in a fixed ratio represented by those green dots up there. If you grind up chloroapatite and sprinkle it into the rock, you will create a mixture between a chlorine and phosphorus-free rock soil, and this mineral that sits along that line. All our chlorine comes from this source. None of it comes from salts that are thought to be what makes the high chlorine on the surface of Mars. Where are those salts gone? The same thing is true of the zinc. Zinc correlates very nicely with iron plot over here. These are the sugartite meteorites over here. These are our analysis over here, and all the Martian soils. This is a logarithmic plot, so there are about 500 versus 100. They're about 5 times higher in zinc. And the reason they're so much higher is that volcanoes exhale elements like sulfur, chlorine, and zinc into the atmosphere, and they recondense to the soil. You don't see this in soils on Earth because we have rain on Earth. The rain dissolves the chlorine, the sulfur, and the zinc and washes it to the ocean. And so the ocean is salty with salt. Now, if you go to the Great Salt Lake in the desert of Utah, you see a sandy surface covered with dry salt crust everywhere. Mars is a lot like this. So Mars must have had an ocean on it at that time. So that liquid water on ancient Mars is required to remove these elements from the ancient soil and then store them in some kind of body of water. Somewhere between the time this meteorite formed and the modern era, that ocean disappeared. It's all dried up. You can tell there's no ocean on Mars today. What happened to all that salt then is it got blown all over the surface by the wind. There are dust storms that cover the entire surface of Mars at least twice a year. And those dust storms would have distributed the salt into all of the rocks and formations that make up modern Mars. And so the difference between modern and ancient Mars is in whether it had water or not. And so this is evidence that we had water at the time. Now, there's independent evidence coming from rover missions as well as from orbiters that find that right where that zero line is on Mars, the ancient cratered highland gives way to the lowlands, and where it does, it seems that deltas, river deltas come, they disgorge sediments, and then they disappear into that big, flat northern highlands that you see. This is the southern highlands, that's the flat northern. It would have once been entirely water covered, and the ancient shoreline can be mapped on Mars. And this is an artist's representation of what the planet might have looked like at the time it had water on it. So it once was a very habitable place. It must have had a much thicker atmosphere because without that, this water would freeze instantly. And so you had clouds, probably of water vapor, and you would have had a carbon dioxide nitrogen atmosphere, much thicker than the one you have today, maybe as much as the atmosphere of Earth. To find out whether Mars was once a water world, we need to go to the rock record. We have now got one sample only that tells us a pinpoint in time at which we say water before, no water afterwards. But we don't know exactly where that transition was, so we need lots of rocks back from Mars. How do we do that? Before I go on, I will pay tribute to Mark Twain over here. And in the course of scientific controversy in the 19th century, Mark Twain made this famous comment. There's something fascinating about science. One gets such wholesale returns of conjecture out of such a trifling investment of fact. So, if we're to go beyond the trifling investment and invest more heavily, we need to have more data. And so to get more facts, we either need to declare war on Mars. That is, we've got to get the US military involved. I mean, they're the only guys right now on the payroll. And they're the only guys who have enough money. I don't know if they have a mission yet, but perhaps we can have terrorists on Mars or something and have them go invade Mars and bring back abundant samples that allow us to make these kinds of studies. And to spend billions of dollars, of course, doing that. But you can tell that the funding climate in Washington these days is not permissive of that. So the alternative plan is to bring back rocks from Mars by the strategy of bateau on a camel. Hunt for meteorites. Because where there's one, there's got to be more ancient meteorites, and we've just not recognized them. Ancient Martian meteorites in the Earth's desert. And we can thank Marvin the Martian, or the impact process, for returning these samples to Earth. And I thank you, of course, for your attention. If you have questions, please feel free to ask them. Afterwards, we will go to the back where the microscope is, and you're welcome to go back there and take a look at the sugartite that's sitting under the microscope. We have a couple of other meteorites on the table there. Bernard, if you would deploy them to the microscope, that would be great. If you want to ask questions, please feel free.
Could you explain the mechanism by which a rock gets from Mars to Earth?
Uh-huh.
And why Earth? I mean, Earth is just a little bit of the area around Mars. So rocks must be, from Mars, must be everywhere.
You're quite right. And one of the conjectures that comes out of this is that if you had had life on early Mars, you could have spread it all through the solar system, because as you impact, Mars is close to the asteroid belt, so you get plenty of impacts on Mars, and those rocks all spiral inwards. It's hard to get them out to Jupiter, but it's easy to get them into the inner terrestrial planets. And so we constantly have rocks coming from Mars. They hit Earth. They must fall on the Moon too, but if you see how hard it is to find them in the Sahara, imagine how hard it is to find them on the Moon. All right. When the Apollo astronauts went to the Moon, one of the fears was they would pick up too many meteorites and not enough moon rocks. And so they were specifically trained in how to avoid picking up meteorites. The result is that in the thousands of samples that came back from the Moon, there are only 2 meteorites. You can't stop an astronaut from making a mistake at least twice. All right. Now, because there are so many, Earth just gets them by accident. The ones that are not collected on Earth, eventually, if they don't hit Venus or Mercury, they're going to fall into the sun. So we're doing them a favor by collecting them.
My question is going to be, is there any way to get Mars into more equitably distributed missiles?
You mean sample?
Martian meteorites in Florida.
Yes, there are likely to be Martian meteorites falling all over. Yes. So the question was, can we get Marvin, that is the distribution process by which meteorites are sent from Mars to Earth, to distribute these meteorites more evenly on the surface of the Earth? Now it turns out, statistically, they must fall everywhere. The reason we find them in Antarctica is so easy to go to Antarctica. You've got this white snow everywhere, and if you find a black piece of rock sitting on that snow, you go and go, wow, meteorite. And every time you collect thousands of meteorites, a few of them will be Martian meteorites. So it's a matter of that they are rare among meteorites even. Sahara Desert has become this next big place, but most of the meteorites, 2/3 of them, fall on the ocean, and they'll never to be seen again. Now, they also fall in the farmlands of America, and they could collect it pretty quickly. There are several of these, and they end up at the Smithsonian Institution. But yes, even Florida must have meteorites, and even Martian meteorites.
You mentioned that there was oceans on Mars. And obviously over time, they disappeared, I guess, because of the atmospheric pressure. Is there any mechanics that change on the surface of Mars that cause evaporation of water?
Yes. So I'll repeat that question. Why did the oceans of Mars disappear? What we know about Mars is that because it lacks a magnetic field, its atmosphere is under constant bombardment from the solar wind. The Earth's atmosphere also gets bombarded by the solar wind, but we have a strong magnetic field. That causes a magnetosphere to form around the Earth, and you can think of that as a force shield. You know, similar to what Star Trek would do. You put up the force shields and stop the phasers from hitting you. Because of that, when particles come from the sun, they can only enter at the poles, and they form these sheets of current that descend into the atmosphere, creating these brilliant lights called the aurora borealis and the aurora australis. Those are the only places where the ions from the sun enter the atmosphere, and so they do very little damage to our atmosphere. By comparison, Mars has no such protection, and so those ions bang away on the atmosphere of Mars, and they thin it with time. And as it gets thinner, the pressure falls at the surface. This causes the water to evaporate, and when water gets up into the stratosphere, it's broken down by ultraviolet light and into hydrogen and oxygen. The hydrogen atoms are very light, and they escape Mars's gravity much more easily than they escape on Earth. Earth too loses water, but it loses it very, very slowly. And one thing that really helps us is because our temperature at the surface is so low, we have a very nice climate. If we overheat the planet, this will change. But right now, as water vapor from the Gulf of Mexico rises up into the atmosphere, cools, and it rains down, and it freezes by this part of the atmosphere called the tropopause. If it wasn't for that freezing, water would get up into the stratosphere and we would lose our oceans a lot faster despite the protective magnetic field. So a combination of cold temperature and a magnetic field saved us from becoming what Venus has become. There's a gentleman over here who's been asking a question for a while. Go ahead.
A couple years ago, there was meteorite from Antarctica that had fossilized organisms. Whatever happened with that?
It's still there. It still has fossilized organisms. Okay.
They were still thinking about it.
Well, there are two schools of thought on this. What you find in there is not really fossilized organisms. What you find are these little magnetic minerals called magnetites. And in their crystal shape, they look exactly like magnetites made by bacteria on Earth that use these magnetites as magnetosomes. They orient themselves in the magnetic field to know up from down, left from right. And they live in very nasty places where if they move a little bit into the wrong neighborhood, they're quickly destroyed. Now, to find them in this meteorite indicates there must be magnetic bacteria on Mars. That is, if they were formed on Mars. So the two schools of thought are, they were formed on Mars, there's life on Mars, or was life on Mars, and we found evidence for it. The other school to which I subscribe is, there's no life on Mars, and these are actually magnetic minerals made by bacteria, except they spent 13,000 years in Antarctica. And they're always found on the outer portion of the meteorite, never on the inside. So I think they're places where bacteria got into the carbonates, ate the minerals, and formed magnetite. They colonized it. It's Earthlings colonizing Mars. Now, one of the evidences that supports that is that there's bomb radiocarbon. Bomb radiocarbon is the excess radiocarbon made in the atmosphere by nuclear testing done in the 1960s. And you can see this excess radiocarbon sitting in this meteorite, even though the meteorite's been 13,000 years on Earth. All of the radiocarbon that was formed on Mars has decayed away. And so finding radiocarbon in it indicates that things are getting in from the atmosphere, and where radiocarbon gets in, so do the bacteria. So Earthlings are very enterprising. Further questions?
If you can't use a compass on Mars, how do you navigate? If you can't use a compass on Mars, how do you navigate?
Well, there's so many satellites from the European Space Agency in the United States around that you can use GPS now.
Does Mars have plate tectonics like Earth does?
Mars tried to have plate tectonics. And this is where it did it. It has this volcanism. You can see this giant crack. This is the Valles Marineris. It's a canyon that is, if you put the United States, it would go from California to Florida over here like that. That spans the whole I-10. That's how big it is. Now that is the scale of the kind of rift systems that we have on Earth. The beginning of plate tectonics. But Mars got arrested. In its early youth, it was caught trying to do plate tectonics until stop. The Earth, on the other hand, was not so obedient. It ran back to the closet, continued to do plate tectonics till it became such a bad habit and never lost it. All right, further questions? Gentleman over there.
Any theory why Mars didn't have a magnetic field? Do you have any theory why Mars didn't have an iron core and a magnetic field? Or
it has an iron core. Why does it not have a magnetic field? So among planets, the inner planets, the 4 inner planets, all have iron cores. Of them, the Earth is the only one with a strong magnetic field. And we think that one of the reasons is that plate tectonics plays a role. To make the magnetic field, you need to cool the core so it crystallizes iron crystals that then go settle on the core mantle boundary, and they release light element that then floats upwards. And you create this circulation that happens then in the core of the planet. And whenever you circulate a electrically conducting fluid, if there's any kind of magnetism around, it amplifies it and makes a magnetic field. So Venus and Mars, lacking plate tectonics, don't have a way of triggering this mechanism in the core. That's what we think happens. But because it happens 3,000 kilometers below our feet, we never get to really test that theory very thoroughly. Okay.
you want to know why do you have sun planets and non-buildings?
So you want to know why there are southern highlands and northern lowlands. And the answer is this. It's got to be a speculation because originally the entire planet must have been covered with a southern highlands kind of crust. But it's thought that a large impactor came in that hit the northern hemisphere. And you can see that in the topography of the rocks over here. When you have such a big impact crater, it doesn't form a ball any longer because the planet will re-deform to fill the crater floor. But the crust that was present will get tossed into these regions, and you will create a topographic low, go high, and then go low again, or go less high over here. And you see this in the areas immediately around the northern lowlands, and that indicates that there's quite likely a large impactor came in and blasted away the old crust. What was left of the old crust then settled down to the crater floor and got covered with sediment coming out during the early phase when you still had running water. And you can see that. You can see these river channels even at this global scale. You see a river channel over there, you see river channels over there, and they disgorge sediment into the northern lowlands and then cover that area so you don't see the impact craters just prominently. But if you look in gravity at the northern lowlands, you can see like where Viking 2 is, there's an old impact crater there, the floor of which you can still recognize in the topography. You can see another big impact crater over here. This is the Hellas Basin. All of that material was blasted out by a large impact, and some of that blasted material, of course, went all through the solar system, but it landed on Earth so long ago, there were no Bedouin to pick it up. Other questions? Over here.
What's your opinion on Mars 1? Are you familiar with the program Mars 1?
The one that did not make it to Mars.
Not yet.
Tell me more.
It's a program to form permanent colonization on Mars by 2023.
This is Zubrin's program.
Whose program?
This is the guy named Zubrin who wants to colonize Mars.
I'm not sure.
Okay. I'm not following that development very closely. So there are private industrialists who want to go to Mars and colonize Mars. And do they have the willingness to put the kind of money that's needed? What would happen if they actually got there and lost their first colony? Well, there'll be some interesting challenges. I don't follow that very closely, but if you know more about it, you might want to talk to us sometime.
Future Science Cafe.
Future Science Cafe. There is a question over there.
So the composition of this hypothetical ocean on the northern side, does it have any sediment that can be measured?
So far, none of the sediment has been brought back by meteorites, but we expect that sooner or later a sedimentary rock from Mars will be found. The problem is, when you pick it up, you won't recognize it's Martian. And if it's full of salt, I'm afraid it will dissolve on Earth. And this is a problem with some kinds of meteorites. They last like days on Earth before they disintegrate into clay. So that's the risk. But yeah, we're really looking forward to finding the first sediment from Mars. And of course, you can do that by going and directly sampling Mars, because there's no better way than picking it up in place. But that's the $100 billion plan. I'm still working on the cheap one. Any other questions?
Another question.
Is there any evidence that Mars was larger in the past, maybe lost some of it from a large impact?
So the question is, was Mars larger in its radius? Well, the amount of Mars we think has been lost is on the order of only a few percent of its total crustal mass. And so the answer is probably not enough to be able to appreciate from a perspective like this. But when if that was a big impact in the northern islands, a very large portion of the crust would be blasted off into space. It's too bad there weren't anybody around to collect it, because that would have been the time to find Martian meteorites. It's probably about 4 billion years ago. Oh. Other questions?
What are some of the big advantages of measuring a sample here on Earth versus measuring it with Curiosity on Mars right now?
Okay, so The big things that you can do in labs on Earth is measure things like radio ages. Right now, Curiosity doesn't do any of that. The other thing you can do is you can measure the trace elements, like iridium, for example. It's very diagnostic of meteorite impacts. Curiosity shows the high nickel, but the nickel is ambiguous in how you interpret it. And so nickel alone has not helped people say this was definitely meteoritic. Now that we have a sample here, we can tell our colleagues in the Mars rover teams and the Curiosity team exactly what they're looking at. There are other things we can measure. I can get into details afterwards. Things like scandium that help us understand why calcium, for example, is depleted in the Martian crust. Anyway, that was the last question. If you want to ask questions, I'll be around for a little bit longer. I'm going to get some dinner and a beer here too. And back over there will be the microscope, and we'll be showing samples. So please come by for a one-on-one, and thank you for listening.